Okay. So, today is 5th lecture. Okay. So, what we had done last time is we had taken a small parallelepiped out of a body and then of size dx dy dz. Is it okay? One small brick from the big body has been taken out, very small, and then here I had introduced the concept of finite size. There is a difference between infinitesimally small size and finite size. If it is a finitely small size, then stresses on positive and negative phases will be same. If it is of a finite size, then left to right there is some distance which is measurable. So, there will be some change, and change means delta of that quantity, and delta means with respect to that distance, I mean that coordinate in which you are moving, and because every quantity is a 3 dimensional. So, there will be a partial derivative rate of change of that quantity multiplied by the distance moved. So, this is what is the concept. So, we had I had already shown you one element on which all the faces were subjected to I mean the the negative faces were all at x point x, and positive faces were all at, so this point and this point, this is what we had taken, no? These were the 2 points, and then all the positive faces were at a distance dx plus, sorry, this was the negative faces are all at point 0, yes, origin, and then this positive faces means this face and this face, front face, they are all positive faces, they are at a distance dx dy dz. So, the coordinate of this point is 0 0 0, while this coordinate is delta x, delta y, delta z, and so on a negative phase all the stresses are the shown here, they are positive stresses, and on positive phases the stresses shown are with a dash quantity, and the meaning of dash is this. Dash means on a x phase it is like this, on a y phase, for example, if you want y phase which is the x phase is this, y is this. So, let us take y z. So, for example, tau y z dash is tau y z, means this one, this quantity on a positive phase. So, it will be tau y z is here on a negative phase plus some addition. Some addition means some delta change in that value, and that value will be delta tau y z with respect to y to delta y. And similarly, if you take any quantity on z phase is this. So, z phase means it is moving from here. So, tau z for example, tau z dash is tau z plus rate of change of tau with respect to z. So, like this, and then under the action of all these tractions means any quantity, any force system that acts on a surface is called traction. So, all these stresses are traction. Stress quantities are also called traction. Stresses. Yes. So, these tractions are stresses that are acting on the positive and negative phases are shown here, and the last time we had taken summation of all forces in x direction, and we got one equation last time by summing all the forces in x direction, by summing all the forces in x direction. That means this is the parallelepiped which are subjected to this plus this. See, I have put here plus, it is not individual. See, both are on the same element. Only thing here it is a negative and here it is positive. So, this element is in a state of equilibrium. So, I must sum, if you sum all the forces in x direction, the sum must be equal to 0 if it is in a state of equilibrium, and last time we did it and we got one equation, that is del tau xx by del x plus del tau yx plus del tau zx. This I had done it fully by explaining the complete diagram. This is the last time, so I am saying that slide is not with me. Plus, if there is a body force means self weight of the element. If Bx, By body force we had taken, that body force consists of three quantities, three components, Bx, By, Bz. B body, it is a vector, three components. So, then Bx, By, Bz. So, then plus Bx, body force, what is the unit of body force? Yes, body force is always per unit volume. That came out to be 0. This was one equation. Incidentally, supposing you are talking of this body was in a state of motion, I am just giving you simply, if the entire body from which you have taken this element, it is in a state of motion with acceleration, motion means what? Not with constant velocity, there is some change in velocity. So, with acceleration a, and a is the acceleration. If acceleration is a is a vector, again this has got three components. It can be acceleration in x direction, acceleration in y direction, acceleration in z direction. So, three components. So, you will get, and if density of the body is rho, then right hand side, from D'Alembert's principle, now what happens, the body is moving in x direction, body. So, there will be a what? Inertia force, that because of the motion, inertia force is put on the body, and then we treat it as a static problem. The inertia force will be mass into acceleration, which will be opposing the motion. So, it will be negative direction. So, this minus the inertia force will be rho times acceleration Ax, must be equal to 0. So, if it is in a dynamic equilibrium, so instead of 0, it becomes rho times Ax, or rho times, if u is the displacement in x direction, then acceleration will be u double dot. U dot will be velocity, u double dot will be acceleration. So, it can also be written as rho u, if u, v, w are the displacements along x, y, z. So, it can also be written like this. So, do not get, so we can also give you the condition for dynamic equation of equilibrium. So, the only change that comes, instead of 0, you get rho density multiplied by acceleration on the right hand side, nothing else. So, okay. So, similarly, so this is the first, this we have already done. Now, I do not want to repeat this for y and z direction. So, if you do in the same way in y and z direction, so you will get this. Okay. So, if you do the summation in y direction, you will get this. Please note that it is very simple, easy to remember. This is here, it is tau xx, that is the on a positive phase S, the stress that is acting in x direction, on a positive y plane, but the force that is acting is in x direction. So, y x. Similarly, on z plane, what is the force that is acting on x direction? Of course, there was a volume that came out, throughout. So, that is why. So, this one will be like this. Similarly, in y direction, everything will be that last subscript, second subscript will be all y. So, it will be x y with respect to del x, then y y with respect to y, and then z y with respect to z, then b y, and if you want dynamics, so it will be rho times v double dot, and similarly z if you take, so it will be this. So, we have got three equations of equilibrium so far by taking the three summations in x, y, z. Now, this element is not infinitesimally small, it is not a point, it is not a point P, it is a referring to, we are talking of P and Q, which are at distance dx, dy, dz. So, it is a finite element, and finite element means it can have rotation. So, your element, when it is in state of equilibrium, it should not also rotate about x, y and z directions. So, rigid body, it is a rigid body. So, next one, now for you have to keep this diagram in front of you, then only you can do. So, this diagram is there, and then you please take moment of about x axis. How do you take moment about x axis? So, if this is x axis, so which are now we go now simplest is I consider now what is there here sigma y is acting here and sigma y is acting here, is it not? So, that will try to rotate the element in clockwise. Now, anti-clockwise will be this. See, this is parallel to x axis. Anything with this second subscript x means it is same direction. So, that will not have any moment about x axis, because that is parallel to x axis. So, you look for quantities which are not second subscript is not x direction. So, I am now looking for this on a negative phase, this is my negative phase y, I am taking tau y y. Tau y y is at a distance dz by 2, and tau y multiplied by the area will give you a force, multiplied by dz by 2 will give you a moment that is anti-clockwise, and that is in a positive x direction. It is anti-clockwise all right, but the vector is in positive x direction. So, I have taken that positive. So, sigma y or tau y y, see sometimes I will be using sigma y and sometimes tau y y, both are same. So, this multiplied by the area of the plane on which it is. What is the area of the plane? It is this area. So, what is this area? This area is dz, and then this one is dx. So, dx dz is the area. So, this becomes force, this total thing becomes force multiplied by the lever arm. What is the lever arm? It is from here, it is acting at a distance dz by 2. So, dz by 2. Now, you always take pairs of forces, it is easier, you know. So, if you have taken negative here, negative plane, please take positive plane here. So, positive plane is sigma y dash, dash means incremental value, sigma y dash is this quantity, again dx dz same, and dz by 2. Which is the other force? Yes, even this one will, this one also will give you moment, dy, which one? But what is interesting is this dyz, which is, see, this is plane and this is x axis. So, one dyz is there, dyz is like this. Now, that will cut this axis. So, that will not give you any moment, but which is at a distance from here to here, dy, there is a dyz, that will give you a moment. So, that is what I have taken. Now, this is dyz dash, dash means incremental, which quantity? It is this dyz, not dy, this, where is dy? Here, here this, see, this dyz will not give you any moment about x axis, because it will cut this axis. But then this dyz here, you know, because this is negative plane and this is positive plane, they are acting on the same, both are same, element is same, it is one element, only thing forces are shown at two places, here negative plane, here positive plane. So, dyz dash multiplies by dx, yes, this is the area, and what is the lever arm? Delta y, total, full, and direction is along x. About this axis, this will turn, and so vector will be in x direction. So, you have to see. So, all vector along x is positive. I think this is all. So, this phase is over. I think this phase means y phase. There is no other force out of 3. We have taken this. This is in x direction. So, this will not produce anything. Again, this is not producing anything. This is not producing anything. And we have already taken this tau y, and then, so I think everything is over. On y phase it is over. Now, please go on z phase, please go to z phase, sigma z, this is negative, this is positive. So, sigma z, yes, sigma z, this one, sigma z multiplied by this dx dy area, that is a force, and this is the sigma z, and what is the distance from x axis? Dy by 2. It is in the center, here, this is dy total. So, dy by 2. So, it is pure geometry and very careful diagram, and please understand, and then you take the moment. You have done more difficult things. Now, this is negative plane. Now, similar thing will also happen at sigma z dash. Where is sigma z dash? positive plane, sorry, yes, this is negative plane, this is positive plane, z, z is this one. Now I am talking of this z dash, again this area multiplied by dy by 2. Okay. Now what else is producing? What else is producing here? Zx will not produce any. Zx will not produce, so zy. Why not zy? Because it is cutting x axis, perpendicular to x axis. So not this, but it is this one, zy dash. So zy dash multiplied by area, and what is the lever arm? Sigma z, dz, from here to here, dz, sorry, dz is correct, dz. So y plane and z planes are over, I think, yes, there is no other force on y plane. See, first we started with y plane, then now we have taken z plane. Z plane, there are only two stresses which will cause moment about x axis. Now we go to x, x plane. I think I don't know, I mean why I took x in the end. I think the reason is there are more forces on x plane which will be giving moment about x axis. Now first start with negative plane, x negative is this plane. Take xy is this component, going in this direction, xy. So xy multiplied by the area of this, area is dz dy, and what is the distance from this x? Yes, no, xy, delta z by 2 I have written, but is it correct? I have written delta z by 2. xy. Yes, it is at the center. This is x axis corner, it is at the center. This distance is dz by 2. And direction also is correct in x direction. Then next force is xy, xz I have taken. Xz is this. Xz is okay. Xz is okay, that will produce a negative. So xz multiplied by this area, and the distance is dy by 2. Okay. This is also correct. Then similar thing, you xy dash, you please take the now positive plane. This was a negative back plane. Now you please take both these xy dash. This is xy dash, this front. So xy dash multiplied by dy dz, okay, dy dz is this is dz and this is dy area, and the distance will be dz by 2. Same, it will be same as this. xy and xy dash, the lever arm has to be same. Then what is the other one? xz dash similar to this, y and z, and again lever arm is this. Only thing, xz dash is producing a positive moment. Is it true? It is producing a positive moment. xz dash, yes, huh? Yes, because it is at a, see this is the center of the element, na, center of the element. So, that is from here. So, that is and this is going like this. So, this will give you a moment that will be vector will be in the positive. So, up to here it is okay. We have taken care of everything. I think something no, okay. Then what about body forces? Body forces, they are all acting at the center of the element. Total weight, total density. So, density multiplied by, I mean, body force per unit volume into the volume is dx dy dz, and about x axis. So, first I have taken by multiplied by dz by 2, it is correct. Sign, you just check up sign whether it is right. Y is, yes, so negative is correct, because y is similar to this one tau y. So, this is, and then bz is upwards in the center of the element, upward force in the center, yes, bz positive. See, these are assumed positive in x, y and z direction. So, this is upward. So, this will produce a moment like this. So, plus this into volume multiplied by this. So, this many terms are there. So, please do not miss any term. It is some people write, when I give them proof that by moment equilibrium you get the following result. The taking moment about x axis, final result, no intermediate calculation. Yes, final result anyway you will get, but how you have got it, that must be shown. So, okay. So, now please see this sigma y into dx dz square by 2. I am taking as it is. See, these are all small quantities, multiplication of small quantities we will have to see, something will come. So, dz square by 2, then sigma y dash is nothing but sigma y plus this multiplied by dx into dz square by 2. Then yz dash is here, next line you see, yz dash equal to yz plus the derivative of this additional multiplied by dx dy dz, it is complete. Then minus sigma z into dx dy square by 2, yes. Then this one is sigma z dash means it is in incremental quantity. Dash you understand, na? On a positive phase, what is the value of stress? It is the, yes, plus increment. So, this is plus increment is this multiplied by dx into dy square by 2, dx dy square by 2. So, we have come up to this point. Now, this is remaining. So, we go to the next slide. Okay. So, then now please see up to we have taken up to this term, yes, sigma z dash. Now, tau z y dash. So, tau क्या हो गया भाई, continued from 6 तो ठीक है, sigma z is over. So, after sigma z zy, now zy को मैं x y z कैसे कर दिया, one line is missing. See, it is a clumsy affair. You have to take every term. So here sigma z, this sigma, this and this was taken. Then what is zy? Why I have not taken this? I am just wondering, because I have written here from slide 7, slide continued from slide 6 of slide lecture 6, ठीक है, but then I have missed something. I think I have missed something, huh? Because this one is saying only this from here, xz dx, this one xz into dy this, yes sir. So actually I have done this here, then I have done this by, then I have done bz, and why, how come I have not done this? That means 1, 2, 3 and 4. Now let us see, there must be some reason. One line I think I have missed out. Anyway, finally I think this is correct, this big bracket and whatever I have written here. These are the terms that are remaining, multiplied by dx dy dz equal to 0. Final. I must have done this. I mean, because this is not given in any book, so you have to do it yourself, you know. So, because this is very. So, this is a big bracket and inside these are the terms, and we have taken common dx dy dz. Everywhere dx dy dz. कुछ तो है, yes. xz, you see what is happening, yes. This up to here we are here na, यहाँ तक. Now this xz dy dz dz dy square by 2, this is the minus sign, and this one will be a, if you expand this will be a plus sign, same quantity. So I think I have shown here that this gets cancelled with xz, this xz here. Similarly this also must be getting, but what about this? That is there, here, that is here. So this is correct. Whatever I have written in the bracket is correct, but then something is missing there. You please correct it. And here, so anyway, these are the quantities. Now then I have written, yes, there are two products, one big bracket and then volume. This is volume. Volume is cannot be equal to 0. So therefore this bracket has to be 0. And since it is involving small quantities, so you have to take the limit of this expression. These are all, there are number of dy, dx, dz. So this bracket, take limit of this, take limit of this as dx, dy, dz tend to 0. So if you take limit of this expression, so whatever quantities, whatever derivative or whatever quantities are having a product of a small quantity, any quantity which is having a product of a small quantity like this, all these quantities b, z, because they are all having, this multiplied by a small quantity. then we are taking a limit of this expression, limit. What when you take limit means, in the limit this we have to put equal to 0. So, all these quantity will tend to become 0. So, what you will be, that is what I have shown here, okay, all these quantities will tend to be 0, and what we will be left with 1 tau y z, yes, here, and there is 1 minus tau somewhere, yes, here, minus tau z y. These are the only quantities without any product of dx, dy, dz. Yes or no? So, the limit, in the limit we are getting that tau yz minus tau zy equal to 0, or this one equal to 0, or tau yz equal to tau zy. So, I have shown this in the picture here. This is x axis perpendicular x y z. About x axis we are taking but this is I have shown only at a point. So, these are the shear stresses that are acting, and this keeps us in equilibrium. Anyway, at any point things are in equilibrium. You do not have to take moment equilibrium, because this point, this is a point. So, this is, so this one, this tau yz and tau zy, they are equal if you take about x axis. So, we got 1. So, x axis will give you tau yz equal to tau zy. Similarly, you take moment about y axis and z axis. It can be proved in a similar, see, if you take y axis, then the quantities that will be appearing will be xz and zx, and about z axis it will be tau xy and tau yx. Is it okay? So, this is about x axis, sorry, y axis, and this is z axis. Z axis there is no z, y axis there is no y, x axis there is no x. It is, this is x axis. And therefore, we can say that any general tau ij is equal to tau ji, I and j both going from 1 to 3 are x, y, z. The shear stresses are complementary to each other. It is also called complementary shear. Complementary shear on two orthogonal planes. So, this is one plane and this is another plane. So, shear over here, this y z and z y here, they are equal to each other, and their directions are more important for you to note. All will not be clockwise or anti-clockwise. See, this is like this, this is like this, this is like this, this is like this. So, this is, so therefore, stress tensor is symmetric. Stress tensor means 3 by 3 matrix which is having 9 quantities, it is a symmetric matrix. So, now only I have proved that there are not 9 quantities, stress tensor is known only by 6 independent quantities. So, this is my stress tensor this matrix arranged, these numbers are arranged in some order. So, this is, there is a main diagonal containing all the normal stresses, and then this is equal, this one will be equal, and again this one will be equal, 6 independent quantities. So, if I now combine whatever we have done so far, so this is a fundamental law of stresses. The stresses at any point must satisfy certain conditions, and what is that certain condition? 3 equations of equilibrium. Stress at any point must satisfy, stress must satisfy the equilibrium condition at each and every point, and that is this. You understand this? This we have already derived. Now, you must write it properly. All these are, this is summation of forces in x direction. So, that is why I have written all x here. This is summation of forces in y direction. So, I have written x, y, y and z, y, clear. And then this is summation of forces in z direction. So, x, z, y, z, sigma z, this. And then there are different ways of writing. In many books you will find right hand side, supposing you can some will write second derivative of u with respect to, for dynamic problem. Right hand side, instead of 0, you can be density times acceleration. What you remember is density times acceleration will be right hand side. So, these 3 equations, 3 differential equations. Why did we get differential equation? Why not an algebraic equation? What is the answer to this? Why have we got differential equation? Yes, because we have considered a differential element of size dx, dy, dz. We want to study the variation of quantity from 0 to dx, 0 to dy, 0 to dz. As we are moving from point P to Q, which are at distance dx, dy, dz apart. So, whenever you consider, see, you can remember, you got also, you derived differential equation in case of a simple rod. If you take a small rod under the action of tension or compression and consider a small element dx subjected to P and P, or a beam also you must have done, beam is subjected to moment, shear, and then this side, it is not only m, we always show m plus dm. It is the same concept. You are going from left face to the right face, which is at a distance x dx. So, there must be some increment. Similarly, shear also increases, it becomes v plus dv, m plus dm. So, here we have 3 equations of equilibrium containing how many unknowns? 6 unknowns. So, equilibrium condition are 3 and number of unknowns are 6. So, it is statically indeterminate of degree 3. Statically indeterminacy. Equilibrium equations are less than the number of stress unknowns. Stress is the here force. So it is statically indeterminate, and somebody asks you what is the degree of indeterminacy. So, it is 3 difference. Okay. So, fundamental problem of elasticity, or any elastic problem is a statically indeterminate problem as such. It is not a determinate problem. So, for statically determinate, I mean indeterminate problem, what is the, what did you do in structural analysis? Yes, you have to study deformation of the body. No, virtually come, that is a different thing. But basic thing is, so far we had considered only a free body diagram of the body in the undeformed state and what are the forces that they are acting on those body. So, for solving any indeterminate problem, you will have to study how does body deform under the action of forces. Unless you study that, you cannot solve. So, any statically indeterminate problem. So, here also so far we did not study deformation of the body. So, you will have to study some state. Of course, not immediately, because immediately I am going to tell you something else. So, this is one very important chapter of elasticity, that is 3 equations of equilibrium of elasticity. How do you write this in tensor notation or indicial notation? 3, all the 3 equations. See, if you want to write down in indicial notation, so let us say first equation I want to write. Now it is tau xx, tau yx, tau zx. So I will just say like this: x is common, then x, y, z, summation over some j, 1 x is common. So I will write it like this: del tau j x, shall I say x, by del x j. So, this will give me this term, these 3 terms. I mean, this is the way it is, del j plus bx equal to 0. Then I told you the other day that differentiation can be written simply by, you do not have to write differentiation. So, j jx comma j plus bx means it is differentiation with respect to this. Now, but then this represents only one equation. This represents, because here j is going from 1 to 3 x, y, z. So, it is giving me 1, 2 and 3 terms and then first line. So, represents only the first equation. Now, I want to represent all the 3. So, it is very easy. I introduce one more subscript. So, it is j. See, do not worry about j or I. I will say here I, ji comma j plus bi. Supposing I just write. So, all this x has become now general bi equal to 0, in which I is also going from 1 to 3 and j is also moving from 1 to 3. Yes. So, this one will give me second equation. this is summation over y, x y z, ठीक है, j is summation. See, since this is repeated, since j is repeated, so it is summation over j. Is it okay? Summation over j. So that means everything, always there will be 3 terms in every line, and then I is a free parameter. I is free, as somebody last time said something else. I is a so in the first line I will be 1, second line I will be 2, third line I will be 3. So you will get all these 3 equations. So a simple equation like this represents all the 3. So you should know what I am saying. Later on, instead of writing 3 equations, we will simply write this. It can also be written, by the way, as tau ij comma I plus what? Bj equal to 0. So, I and j can be interchanged, that is not. Because whenever in any expression there are subscripts that are repeated. So, remember, it means summation. This term is I is going from 1 to 3. So, first expand that, it is going from 1 to 3. Okay. Then what is the effect of stress on any body? Effect of it compresses or elongates the body. So, the effect is a change in volume, if you want to study, without change in shape. One is stress, and then I have written change in shape without change in volume. Shear. So, one is something like hydrostatic pressure. Put a body in water, it will become under compression from all sides. So, one is change in volume, other is change in shape. So, these are the 2 effects of stress. Now, change in volume is similar to hydrostatic type of stress, that is normal stresses. It is also called isotropic state of stress. Isotropic means things are acting in all the directions, same isotropic, no directional change. Iso, in all direction it is the same. So, just like hydrostatic pressure. So, it is also called isotropic state of stress. Change in shape will be caused by shear stresses. So, this is called isotropic state of stress, and these shear stresses are called deviatoric state of stress. deviatoric, deviatoric. It changes the volume, deviatoric state of stress. So, we can write that stress is composed of 2 parts. One is hydrostatic, other one is deviatoric. No, not change the volume, change the shape without volume. Deviatoric changes the shape without volume, and this changes the volume, first part. So, either if you use sigma, it can write like this. If you use tau for every stress component, then this can be written. So, these are two alternative forms, nothing. They are nothing, either replace sigma by tau, you can anything. So, this is all right. This is little descriptive. Is it, this one is clear? I think it is simple. Only thing we should know. So, whatever we know, we are just stating in words. Now, you see whether some results can come out of this. So, if you have this kind of stress, so now I have taken hydrostatic. The hydrostatic means what? As far as tensor is concerned, all the normal stresses must be same. So, let us say is a part of the stress state. So, this one having only constant pressure. All normal stresses must be having the same magnitude, then only it will be no change in shape. If you are having even normal, but different quantities, then there will be change in shape. If you want to avoid change in shape, so they must be all same and no shear stress. Now, the sum of three normal stresses, sum of three sigma x, sigma y, sigma z, tau xx, tau yy and tau zz, sum of three is called first invariant of stress, and I will tell you what is the meaning of invariant later. Invariant means it does not change, the value does not change. So, it is called first invariant, and so I have denoted by first means this capital letter first, sigma hydro, this is the invariant. So, invariant means I have just added sigma x, sigma y, sigma z. So, it is summation of three normal stresses is called first invariant. So, that summation is equal to 3p and that is equal to this or this, the way you want to. So, this is called first invariant of hydrostatic stress, and therefore, P is equal to always, P will be 1/3 of the normal stresses or 1/3 of the first invariant. First invariant is denoted by I, a letter I, invariant of stress. I will tell you, I mean, what is this? The summation of three normal stresses is denoted by a letter I. It is called the first invariant. So, this one will be, and since it is first, so we say I1. So, this is equal to I by 3 and that is equal to, that is right now, do not worry about this because you do not know something. So, the hydrostatic state of stress can be written like this, P will be equal to this. Now, deviatoric deviatoric part will be, I mean, either you denote by this or denote by this, I have just written both, equal to total sigma, total stress tensor minus the hydrostatic. Okay. Since now we have already computed hydrostatic, that is very simple. So, we will just say here it is total sigma minus hydrostatic, and total sigma is this minus hydrostatic is this. So, this is the expression for deviatoric state of stress. This causes change in shape without change in volume. So, if you have this kind of stress, then there is one more type of stress that is important. Octahedral state. What is octahedral state of stress? Octahedral means, first of all, I have to create a plane which is octahedral. So, octahedral body, you know, you have a XYZ and you have, so it cuts the quadrant into top 4 and 4 bottom, and you create inclined plane, triangular inclined plane in all these. So, whatever object solid you get, that is called octahedral. So, in one positive plane, what is, supposing somebody asks you that plane, because it is a very unique plane, all sides are equal, na? This will be then yes, this will be equal, this will be yes. So, I have drawn one out of 8, 1 out of 8. So, its size is a 0 0, this is the coordinate, here it is 0 a 0 and it is 0 0 a. These are the coordinates of this triangular plane. So, once we define this plane, there are 8 such planes. So, many times we have to find out what is the stress in terms of the coordinate plane stresses. What is the stress on this plane? Now, right now we do not know anything, something you do not know, although I mean you know what is principal stress, but in 3 dimension you do not know how to find out principal stress. So, I will complete that first and then I will take this up, because it will require, I have also presented this in terms of, I am saying 1, 2, 3 are principal directions. Principal directions means directions in which stresses are maxima, normal stresses are maxima or minima, 1 maxima, 1, 2 minima. So, I will first now take up what is a principal direction, and then, so this I think will come later. So, what is a principal direction? Simple. You are having this plane at any point which is moving, which has got infinite orientation. There will be one orientation of this plane which is moving at this point, such that on this plane there will be only normal stresses, no shear stresses. So, look for that orientation when you have only, so let ABC, so we call such a plane as principal plane. So, if ABC is a principal plane, means only normal stresses on this plane, no shear stresses. It is the same thing, you have this plane, you just move, go on rotating, there will be one direction something, yes, this direction, you will find this will contain only normal stress, no shear on this. So, that direction is called principal direction. The direction, so this is what I have written here. The plane, when the stress is only normal on it, so normal to that defines the direction of the plane, and that direction is called. So, if let us say ln x, ln y, ln z are that, this is the direction of the plane. then but what about the other? See, that is principal diagram, but then you construct a small parallelepiped there, this plane is there, then this side, and then you close it. So, this is, yes, this is, even on this there will be only normal, even on this plane there will be only normal. So, there will be 3 normal stresses acting at the same point. Now, only thing is all will not be of the same value, some will be, one will be the largest, other two can be, it can be positive, negative also, they need not be all tensile or compression, there can be plus or minus, but they will all be normal. So, there will be 3 directions, that means there will be 3 directions, is it not? One direction you have found out, so that is for, once you have got this direction, so you can also get this direction, next one, and you can also get this direction, so that you complete your complete parallelepiped at that point. So, then, so if that is what I, if you choose the principal axis 1, 2, 3 as the coordinate axis, these are normally principal directions are denoted by 1, 2, 3 and normal axis are denoted by x, y, z. Then the stress matrix has the simplified form because no shear. So, it will be sigma 1, sigma 2, sigma 3. Of course, it can be plus or minus, that I have not shown, but then let us say sigma 1, sigma 2, sigma 3. And one such plane, so this is my one direction, this is 2 direction, this is 3 direction, and this is the inclined plane. Okay. Where is sigma 1? Then sigma 1 will be, yes, in one on this plane. Sigma 2 will be on this plane and sigma 3 will be on this plane. These are the 3 planes, coordinate. So, this is 3. Now, let us say this inclined plane has got a direction cosine n. So, and the direction cosine is ln x, ln y, ln z, sorry, ln 1, ln 2, ln 3, n to 1, n to 2, n to 3. Then the 3 components in 1, 2 and 3 direction of this will be given by this stress matrix multiplied by the direction cosine. So, Tn1, Tn2, Tn3 will be stress matrix multiplied by the direction cosine matrix. This is becoming little, it is over. Okay. Okay, then I will do it tomorrow, tomorrow morning, 8:30.